Hello, Chemistry 30. Today I'm going to show you how to use your redox table to predict redox reactions. Okay, so we've seen how redox tables are made, and a really big one's been made for us. It is in our data booklet. Okay, this is it. You're going to use this a lot in the next 2 weeks or so. All right, it's laid out just like the ones we were making. So the strongest oxidizing agents are on the top left. They go weaker as you go down. The very bottom is your strongest reducing agent, and they get weaker as you go up. Okay, so check it out. Fluorine gas is a super strong oxidizing agent. That means it steals electrons from everything below it on the table. Any of these things will react with fluorine gas. Check it out, including gold. Okay, if you have a whole bunch of gold, keep it away from fluorine gas. Just a tip. Also, keep it away from acidified permanganate. I have some of that. Well, I have permanganate. You acidify it when you want to react it with something. Okay. Similarly, lithium reacts explosively with a lot of things, including water, because it just barely holds on to its electron. It gives away its electron to anybody who wants it, which is everybody above it on the left. Okay, so actually I think you see water is right here. Water spontaneously reacts with all of these guys, mostly what you call like active metals. Okay, lithium, potassium, calcium, sodium, etc. So this is it. This is your data table. We're going to use it a lot, and I'm going to show you how to use it today to predict redox reactions, which is what it's most useful for. All right. So when you're predicting a net redox reaction and its spontaneity, you use the table and these steps. Okay, like when we were introduced to complex half reactions, there are a lot of steps and it may seem somewhat overwhelming at first. Okay, but after a few examples, you just kind of follow the steps without even really thinking about it. All right, so here we go. I'm just going to give them to you, and we'll run through an example. First thing you do is you list every entity that's available in the reaction. That is often the most challenging part for a lot of students. Okay? And I'll give you some tips starting today. You label all of these as OAs or RAs, and you can determine if they're OAs and RAs by looking at your data table. Okay? Then you identify the SOA, the strongest oxidizing agent, and the strongest reducing agent. The SOA will be the highest on the left. The SRA will be lowest on the right. And as I mentioned, right after we go through these steps, we'll dive right into an example, and there'll be another example video available for you today. So, next thing you do is you take your SOA and you write the reduction half reaction as it appears in your data booklet. Let's say you got this hypochlorite in solution. The OCl plus H2O plus 2E becomes this. You just write it as you see it. You don't change anything. Next thing, you write the oxidation half reaction of the SRA. Put it in brackets right to left because oxidation half reactions go right to left. Let's say solid zinc was being oxidized. You'd write it zinc becomes zinc 2 ions and 2 electrons. Okay, you'll see in the example we do, find the SRA and then you write it right to left. Then you have to multiply a half reaction or sometimes both just to balance the electrons. Okay, and the electrons have to be balanced because they go from one to the other, right? You bring them together and some things will cross out. Then you use the redox spontaneity rule to determine if the reaction is spontaneous. This sounds really complicated, but it's very, very simple. If the SOA is above the SRA, the reaction is spontaneous. That's it. The last step is actually the simplest. So, as promised, here we have an example, and I'm going to walk you through absolutely everything. Okay? We've got a solution of zinc perchlorate. It's mixed with an acidified tin 2 chloride solution, which is this. Determine the net redox. Is it spontaneous? Okay, the first thing I'll deal with is this word. You'll see it a lot. That just means that there's acid, so H plus is present. Okay, so what we're going to do, step one, is to label all the entities present. These are things that could react. If something's acidified, we know there's H+. It won't always be available. It'll say if it's available or not. Okay. Another thing that's going to be present virtually every time, anytime you see the word solution or you see aqueous anywhere, that just means that these things are dissolved in water, so water is available. Okay, so those are out of the way. These things are what people mess up with quite often. I just need you to remember an aqueous solution. I'll start with this one because it's simpler. These are dissociated ions. Okay, so tin 2 chloride, aqueous, what it is it's tin 2 ions and chloride ions. I don't care about the coefficients right now. I just care that there is chloride. So I don't need to write 2Cl. You don't need to write a dissociation equation because step one is just to write down what we've got. So we got H+ because it's acidified. We got H2O because these things are in solution. These are dissociated tin 2 and chloride ions. Notice there is no solid piece of tin anywhere. There's no chlorine gas. These are ions in solution. Okay, which brings us to our last one here. Okay, this is getting kind of messy, but that's okay, especially for our first one. Dissociated ions. It's zinc ions. Perchlorate is a polyatomic ion. Do not break that apart. Okay, this is the dissociation of zinc perchlorate. Again, I don't care that there would be 2 of these for every one of these. All we're doing is listing what's present. Okay, so these are the things that we have available for redox. And I think that's it. We dealt with the zinc chloride. We dealt with the fact it's acidified. These things are in solution. Tin, chloride, love it. Okay, what was the next step? We have to identify OAs, RAs, and the strongest of each. Okay, well, you'll get good at this, and it's pretty cumbersome at first. But I want you to see something right away. Check out this guy here, ClO4 plus H+. We have those. These guys together. That's on the left. Together they're an OA. Okay, so we're just looking on the left for OAs. ClO4 H+. We got those. Okay, moving down, I kind of know what I'm looking for, so I'm going kind of fast. I know water is an OA. So I know H+ by itself is an OA. Zinc 2 is an OA near the bottom. And tin 2 is an OA as well. Okay. After some experience, you'll know to just stop when you find the SOA. Like this is our SOA. It's the highest one. Okay. I'll actually save that for after our RAs. I'll follow the steps as I wrote them out. So to find RAs, I recommend start at the bottom and go up. Okay, so here's zinc. Solid zinc. Do we have solid zinc? No, we do not. This is not a solid piece of zinc. These are dissociated zinc ions floating around in water. This is a solid piece of zinc. We don't have that. Okay, this is not an RA at all because it's not solid zinc. Keep going up. Solid tin. No dice, that's tin 2 ions. But look, tin 2 ions are an RA. And if I go farther up, I see that water is also an RA. I think chloride might be, yeah, it is right there. But the tin 2 ions is going to be our strongest Ra. And I'll just briefly discuss what makes them the strongest. Whatever's highest on the left is your strongest Ra. Definitely perchlorate with acid. There are very few stronger OAs than that. And then whatever is closest to the bottom on the right is our strongest Ra. Right here, tin 2 ions. We don't have any of the things below it. All right, so now I've got to write out some half reactions. This is how I do it. I label my SOA. This is going to be a reduction half reaction. Again, just write out exactly what's in your data booklet. So spend a minute doing that. Cool. Looks great. Now I write out the oxidation half reaction of the SRA. Now this will be a bit harder to do picture in picture. I gotta go right to left. So that's gonna be tin 2 becoming tin 4 and 2 electrons. Luckily that's easy to remember. Okay, so tin 2 becoming tin 4 plus 2 electrons. You write the oxidation half reaction of the SOA right to left. There's my 2 half reactions. Now we're kind of in cruise control. All right, next step is to multiply half reaction to balance the electrons. And this is usually not too challenging. Look at the electrons, I got them lined up. The perchlorate needs to gain 8 electrons with acid to undergo redox. It has to get them from the tin 2. This reaction's got to happen 4 times in order to balance these electrons, right? Because 2 times 4 is going to be 8. All right, so what I'm going to do is just multiply everything by 4. All right, now we just bring these half reactions together, the ones with the balanced electrons. And it becomes our net when we cross some things off. So all I'm going to do, it's going to be pretty wild. I'm just going to write down absolutely everything. I've noticed I've neglected some state symbols. Let me demonstrate I have good habits. Okay, so what I have here, just all the reactants once we've balanced the electrons. So I'm not using this one anymore. This one I've multiplied by 4 to balance the electrons. So that's why I got 4 of these guys. Then the products are just these products and these products. Okay, at the very least you'll be able to cross off some electrons. There might be some other things eventually, like some water or some H's and OH's coming together. But definitely the electrons have to be crossed off because they have to be equal. That's the whole point of the previous step. Okay, let me actually finish this on a fresh piece of paper and it'll look really good. Okay, so here's our net redox. Okay, so that's it. It's always a great idea to just check if things are balanced. I mean, I usually just stick to the charge. Let's see here. I got +8, +8, -1. I got +15 on the left. I get 16 from here, -1, +15 on the right. Really good indication everything's correct. You can balance your other atoms if you want. 1 Cl, looks like I got 4 oxygens, that's looking good, 8 hydrogens, 4 tins. We're good. This is balanced. All right. All the hard work's over. The last thing is just to determine if it's spontaneous based on the redox spontaneity rule. And I'll just remind you, all that rule is saying that there's a spontaneous reaction if the OA is above the RA in the table. Well, my SOA was all the way up here. My SRA is down here. Anytime the OA is above the RA, that's a spontaneous reaction. The nicest way of just indicating that, all I ever have to see is you write the word spawn above the arrow. If it was not spontaneous, you could write non-spawn, and I'd be really happy with that. All right, I really hope this helps. You get good at this by trying it. Good luck out there.